All right, today we're going to look at rational exponents. Rational exponents. What we're able to do, and this is probably a review. I'm sure you guys have seen this in the past at some point, but we're able to convert radicals into rational exponents, and frequently that's a useful thing to do because it makes the algebra easier. We can then use all of our properties of exponents like we've done in the past. Okay, so how do we do this? Well, in general, let's start with this one because this is the general one. If I have the nth root of a to the m power, okay, then how do we write that as a fractional exponent? It's pretty simple. What happens is the index of the radical always goes to the denominator of the fractional exponent, and the power of the base inside the radical becomes the numerator. Okay, so in general, a to the m over n power corresponds to the nth root of a to the m. Now you have the option, there's two ways you can do this. You have the option of either taking a to the m power inside the radical, or you could do the nth root of a all taken to the mth power outside. So the m could either be the power of the entire radical or just the a inside the radical. They're perfectly equivalent, mean the same thing. As we'll see, it just depends on the circumstances, but sometimes one way is more convenient than the other way. Let's take something, and then, so what about the top example then? The nth root of a is just a to the 1 over n, because what's the power of a inside the radical? It's invisible. No, inside the radical, what's the power of a? It's a 1, isn't it? It's a to the 1, so we've got a 1 in the numerator in that case, right? If it's just a plain old nth root, then it's just the power 1 over n. Okay? Give me 1 to 5. How are we doing? Okay? All right, so let's practice this a little bit. How about 24 to the 1/3 then? That's an example where it would probably be a little bit more convenient for us to just turn that into a radical because we know how to simplify. We know how to simplify roots of numbers pretty easily, right? So what would that be as a radical? Yeah, it'd be the cube root of 24. Good. And then you guys have had a ton of practice already doing that. How do we simplify a cube root of 24? What do I have to do to the 24? Yeah, go ahead. Yeah. So I got to make a factor tree, right? What's 24 going to factor into? 8 and 3. And then 8's going to break up into what? 2's. I'm going to get 2 times 2 times 2. So that's giving me a triple 2 and a single 3. And we have to use a slightly different saying for a cube root. Instead of couples go out, singles stay in, what do we do for a cube root? Triples go out, everything else stays in, right? So in this case, then we get outside, we get a 2, inside, we get a 3. Okay, no big deal, right? What about something like 27 to the 2/3? What are my options here? How could I rewrite that as a radical? Cube root of, okay, there's one way to do it, would be to write that as a cube root of 27 squared. Another way to do it would be what? Okay, cube root of 27 quantity squared. One of those is definitely better. Which one, red or green, is better? Green, for sure. Right, the red one's kind of tough. That's giving us, if I want to take that route, I've got a cube root of some really big number, which is doubly problematic because A, I've got to figure out what 27 squared is, which we don't just immediately probably know, and then I've got to take a cube root of that very big number. Neither one of those things is intuitively obvious to do, probably, right? So that's not a great move. Bottom one, on the other hand, is a great plan because what's the cube root of 27? 3 squared is 9, easy. Okay, why is that always better to do if I've got a number to a fractional power? It's always better to do the root part first, the denominator part first, because then the middle step involves small numbers instead of really big numbers, right? So you always want to take the root first, and then whatever that root is, take that smaller number to the power of the numerator, much, much easier, okay? How would we rewrite this bottom expression using a fractional exponent? X to what power? 7/4. Okay, again, we know because the index of the radical always goes in the denominator. That's an easy one to remember, okay? So then how would we do something like that top one? Do I want to convert those to radicals right away? Probably not, right? If I convert those to radicals, they're going to look kind of ugly, right? What would that first one be if I wrote it as a radical? Okay, that didn't sound 3. There's no square roots there. It's not a square root. Cube root of 5x, is it? Cube root of 5x. Give me thumbs on that. I'm going thumbs down. It's not cube root of 5x. What is it? 5 times cube root of x. Because how come the 5 is not in the cube root? How do we know? Okay, good. Because it's 5 times x to the 1/3. If the whole thing were included, I'd have to have parentheses around the whole 5x, wouldn't I? Which I don't have. So this would be 5 times the cube root of x, and this would become what? 7 times the 5th root of x. And what the heck is that? What's a cube root of x times the 5th root of x? That's difficult to do with radicals, right? Okay, but maybe we could make this easier if we don't convert this to a radical right away. It's a lot easier for us to leverage the properties of exponents here, which are easy, right? So what could I do initially up here? What might be one nice thing to do that, oh, come on. Well, how many things am I multiplying in that product up there? You could say 2 because I've got parentheses, but I don't even really need those parentheses. What do you get? Logan, what 4 things? You're right. Both of the powers and both of the coefficients, right? I've got 5 times x to the 1/3 times 7 times x to the 1/5. You're on the right track. So what would be a convenient way to commute those factors and change the order up? We can do that when we're multiplying stuff. Yeah, so how about if we multiply the coefficients first? 5 times 7 is 35. Okay, what about the rest of that then? I've got x to the 1/3 times x to the 1/5. Well, what do we do? We've done tons of stuff like that. What do we do when we multiply powers with like bases? What do we do with the exponents? You add them, don't you? Yeah. So this just becomes 35 x to the 1/3 plus 1/5. I just have to add some fractions up, but that's not a big deal. What's my common denominator going to be here? 15. So what do I have to multiply both the top and the bottom of the first fraction by? Second one? Okay, so that's giving me 35 x to the 5/15 plus 3/15 is what? 8/15. So the last step then, if I want to write this as a radical, I just have to convert this into radical form. Well, I get my 35 is out in front. What does the red stuff become as a radical? 15th root of x to the 8th. There you go. There it is, right? Okay, give me 1 to 5. How are we doing? Okay. All right, what about something like that next one? If I want to rewrite that using a radical, how could I do it? Distribute to 12? What do you think? There you go. I can't do that. Very good. I can't do that because there's an exponent, and PEMDAS says I have to simplify exponents prior to multiplying, right? I can't do that. And it doesn't make sense. If you're ever wondering, that looks like a complicated case where I've got variables and fractional exponents, but always just pick a really simple example to test out your hypothesis. So you're saying, like, if I wanted to distribute, what if I had a 4 times 2 plus 3 squared? Use numbers. Well, 4 times 2 plus 3 is 5 squared is 25 times 4. What should my answer be? 100. Yeah, it should be 100. Okay, but if we were to distribute here, as was suggested, then that would give me 8 plus 12 quantity squared. That's 20 squared, which is 400. Well, that's wrong, right? You can't do that. That violates PEMDAS. So we cannot distribute. The 12 ends up just being a 12 outside, right? What about the other part? What's all this stuff inside the purple bubble going to become? What do you think? Okay, it's gonna be some kind of radical, isn't it? Well, 7th root of, okay, that whole quantity cubed. Good? Everybody buy that? Okay. And then out front, I've just got a 12. Okay. 1 to 5. How we doing? Okay. No, that's best we can do. Best we could do. Okay. Yep. I mean, all we're really trying to do is just write it as a radical. There's nothing else I could do in that case. Okay, how about now the bottom one? Maybe we could do a little better. The quantity 216x to the 15th to the negative 1/3. 1001, 1002. No, is that enough? Okay, all right. All right. So how about this one? What's that negative doing? We got to think of our properties of exponents. What's a to the negative n equal to? Yeah, 1 over a to the n. Okay. So then that negative is just giving us 1 over the quantity 216x to the 15th to the 1/3, right? Okay, now what? What do I do with all that stuff in the denominator then? Okay, I mean, I could make it a big cube root. I can. That's fine. Is there, rather than make that one big cube root, is there something else? Is there a property of exponents? That would work, by the way. That's fine. It looks like I'm taking a product of two things, 216 times x to the 15th, to some power. What's my property that applies there? What's the quantity AB to the m? Yeah, a to the m times b to the m. Now that does not apply, only applies if we're multiplying, not if we're adding or subtracting, right? Okay, but when we're multiplying, yeah, that works. So then in this case, I'm getting 1 over 216 to the 1/3 times x to the 15th to the 1/3. Okay, well, what is 216 to the 1/3? Cube root of 216, which is 6. Aha. So I get 6. And then what's x to the 15th to the 1/3? What is it? X to the 5th. Good. How come? Because what's our property there? If I take a power, raise a power to a power, what do I do with the exponents? You multiply. Exactly. Good. So I get a to the m times n. Hello. Right there. Yeah. Awesome. You bet. Okay, so then that's going to give us down here an x to the 15 times 1/3, which is x to the 5th. Okay, give me 1 to 5. How are we doing? Okay, good, good. So again, are you seeing how these properties of exponents make this so much easier than if you were just dealing with radicals, right? Makes the algebra way, way easier. Okay, what about one like that? Looks complicated as a radical. What could we do there? Matthew, what do you think? Okay, so help me out. What's that going to be then? Okay, so, right. So then all this stuff right here that's being raised to the 4th power, what's that going to become? Twelve over 3, right? You see why? Because okay, good. Appreciate the honesty. Okay, because the index of the radical becomes the denominator and the power becomes the numerator, right? Okay, so we've got all that stuff to the 4th. Okay, well, again, here is where properties of exponents are friends. I mean, well, I guess not property, but just writing it as a rational exponent. What is 12/3? 4. Yeah, look at that. So I'm just getting x to the 4th raised to the power of 4. So what's my answer? There it is. Okay. Piece of cake, right? If you just take advantage of those properties of exponents, piece of cake. Okay, how about this guy? What's the top one going to be? Thaden, what's the top one? Good. So I get W in the top, I get W to the 4/3. Bottom one, 4/5. Okay, what's my property of exponents that I would apply if I'm dividing powers with like bases? Subtract the exponents. So we get W to the 4/3 minus 4/5. What's my common denominator this time? 15. So I'm going to multiply top and bottom by 5 here and by. Okay, so that gives me W to the, I've got a common denominator of 15, and it looks like I'm getting 20 minus 12. So my answer's looking like what then? 8 over 15. Matthew, what's that going to be as a radical? What is it? I got to write it as a radical. I want to write that as a radical. Shh, 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 shh. Okay, so we'd say that the 15th root of W to the 8th. Yes, you're right. Okay, good job. You got it. Okay, so now no big deal. You guys, I'm sure that's all fairly light work, right? But now one other issue comes up sometimes. And that is, I'm going to show you a great trick. So what happens if we're doing this stuff and when we convert a radical to an exponent, a fractional exponent, we get an improper fraction where the numerator is bigger than the denominator. Okay, now I want you to think about this in the context of how we simplify radicals. Like if I give you an example, what if I ask you to simplify the square root of 50? You'll all tell me the answer is what? 5 root 2. Yeah. Okay. Right, 25 and 2. Okay, and what's our goal? When we're simplifying radicals, we want to get as much out of the radical as possible, right? Okay, well, that was easy with a 50. What do we do here? Is there some stuff we could get out of the radical? It turns out there is. So here's the path to get there. It's a really simple way to go. If you write this as a fractional exponent, when the exponent is an improper fraction, numerator bigger than denominator, then just rewrite that as a mixed number. So 11/3 is what as a mixed number? 3 2/3, exactly, right? Because 3 divides into 11 3 times, R2, right, with a remainder of 2. And the remainder is what remains over my denominator of 3, right? So it's x to the 3 2/3. And 3 2/3, I know you guys did this kind of stuff back in middle school. You know, we don't really use mixed numbers anymore, but if we think of this as a mixed number, 3 2/3 looks a little bit misleading when you write it because it almost implies that they're being multiplied, but they're not really. It's 3. How are the 3 and the 2/3 connected? Plus 2/3, right? So we could use our properties of exponents in reverse. X to the power 3 plus 2/3 is the same thing as what would happen if I multiplied like bases and added the exponents, right? That's the same thing as saying x cubed times x to the 2/3. Look what happened. The blue part here, the power that's associated with the integer part of that mixed number, that's just a regular old x cubed that's outside of the radical. It's the fractional part is going to correspond to the simplified radical. What's left behind? X to the 2/3. Isn't that just a cube root of x squared? Right? Do you have to do all those intervening steps? No, not really. I would say it's pretty easy just to go right from here down to here. Right? How come? How do you do that? Well, simple. Whatever the integer part is, that 3 corresponds to the outside power of the base, and the 2/3, look where the 2 goes. Well, the 2 is going there, and we know that the 3 on the bottom just corresponds to the kind of root that we're taking. It's a cube root, right? Okay, so let's try one of these. You guys want to try this one on the board? Okay, go. Try that on the board. There were a variety of different paths people took. I think for the most part, people were arriving at the same place, but let's see how efficient we can be with this. There's kind of a flow to this that makes the most sense. So how about this first radical? That's just becoming y to what power? 3/30. Good. Times, yeah, this guy becomes y to the 41/15. So when we multiply like bases, we add exponents, right? So that just becomes y to the 3/30 plus 41/15. Well, 41/15. What do I need to do there to get a common denominator? Okay, 2/2. And that's going to give me y to the 3 plus 82, 85, over my common denominator of 30, right? 3/30 plus 82/30 is 85/30, right? Okay, now what should I probably do? Say it again. Simple. You mean reduce the fraction? Yeah, that's what I would do. I mean, you could split that up right now. You could make that a mixed number, but why not just reduce the fraction first? So 85/30 becomes what? 17/6. So we get y to the 17/6. Okay, now I've got an improper fractional exponent. So now what do I do? Split it up. Okay, into a mixed number. So what's the integer part going to be? 2. 6 goes into 17 2 times with how many left over? Okay, so now what does that mean then? If we want to convert that into a radical, The 2 part tells me that the power of the base outside of the radical is 2. So what goes outside? Y squared. What does the 5/6 tell us? 6th root of y to the 5th. Okay? 1 to 5, how are we doing? Okay. All right, last thing for today, I want to show you. Okay, you're getting the hang of this. Now, when you see something like that, that probably gives you the chills, right? I mean, that looks terrible. I've got this radical of this great big radicand that includes a coefficient and 3 different powers of variables, right? Okay, it's not hard to do though. All you have to do is split this up into a product of each of those 4 parts done separately. So what do I really have here? I've got the 4th root of 288 times the 4th root of x to the 7th, which is x to the 7/4, times the 4th root of y, which is y to the 1/4, times the 4th root of z to the 18, which is z to the 18/4. Okay? Just deal with them one at a time. And all I'm going to end up doing with each of those 4 factors that I've separated, I'm going to break each of those into an outside part and an inside part and then recombine them into one radical. Easy. So 288 we know how to do. Like if I were to make a factor tree out of 288, what you would find is at the bottom of the factor tree, you get a string of 1, 2, 3, 4, 5 2's times 2 3's. But we're doing a 4th root. So what's our saying here for a 4th root? Whatever you want to call it, fourths or quadruples go out, everything else stays in. So it looks like I've got 1 quadruple 2 and a single 2 and a double 3. So the singles and doubles stay in, the 2 goes out because I have a quadruple 2. Okay, so the number part, I get a 2 outside and an 18 inside, right? How about the x to the 7/4? Well, 7/4 as a mixed number becomes 1 3/4. So I get an x to the 1 outside, and I get an x cubed, a 4th root of x cubed inside, right? What about the y to the 1/4? Well, do I even really need to turn that into a y to the 1/4? I don't really, do I? I don't, because I know that I'm just going to get stuck with the 4th root of y doesn't simplify. I'm just stuck with that y inside. So there it is, 4th root of y. The y is all inside. Okay, last issue. What about the z to the 18/4? Do I want to write that as a 9/2? You're right. How come? How come I do not want to write it as a 9/2? I could reduce the fraction to a 9/2, but what's the problem with that? Okay, that would require a different kind of a root, wouldn't it? A 9/2 would be, that means if the denominator turns into a 2, now it's not a 4th root anymore. Now it's a 2nd root or a square root. And I don't want to write it as a product of 2 separate roots. I want to write it as a radical of one radical, right? So I want to leave the denominators all the same. So what's your rule there? Your rule is only reduce rational exponents if all of the exponents can be reduced to the same denominator. If they all can, then that's fine, go for it. But if they can't, don't do it, right? You got to leave it as the original denominator, okay? So then what happens to my 18/4? Well, 18/4 as a mixed number is 4 2/4. So z to the 18/4, then I'm going to get a z to the 4th outside and a 4th root of z squared inside, right? Then I just reassemble all that stuff. All the outside parts go outside. So I had a 2 outside, I had an x to the 1, and I had a z to the 4th. So my outside stuff is 2x z to the 4th. What's my inside stuff? I had the number 18, I had an x cubed, I had a y to the 1, and I had a z squared inside. So combine it, multiply those together. I get a 4th root of the product of all that stuff. Okay, make sense? No big deal. It's really no harder than what we just did last time. Probably even easier. Okay, do you want to try that? You don't have a lot of time. You want to try that one real quick at the end? Go for it. Go to the boards and try this one.